So, I'm here to welcome you to the second and last of 3 lectures by Michael Friedman. I hope everyone is here for the first 1.5, which will be finished today. Michael Friedman is the Frederick P. Ramus family. No?
Suppi's Professor of Philosophy of Science.
Oh, sorry.
It's changed.
Okay.
Things change.
I will blame Wikipedia. Okay. But enough about you. Let me talk about me for a minute. When I was in graduate school, a bunch of us were interested in philosophy of space and time, which the people there weren't actually that interested in teaching, but we prevailed on Clark Greenmore to do a course, and we did a full-year course. And the first half of it was mathematics and sort of preparation, and then we spent many, I guess a couple months going very carefully through Michael's book on Foundations of Space-Time Theory. And just personally, I wanted to say, it was at that time that I understood how to think about space and time without coordinates, which has more or less been half of my career, telling other people to do the same thing. So I have Michael to thank for it, and it was really an extremely useful way to adjust your conceptual system to think very seriously about ontology as it appears in science. This is going to be maybe a little different, but we'll get the end of the story.
You'll see a couple of the figures from that book.
Yeah.
You already saw them.
So,
Thank you so much, Tim. And I really appreciate you saying that you learned from my book rather than pointing out all the errors in the book. Okay, so today I have no text. I'm going to talk and show you these slides. And what I'm going to be trying to do in this lecture, as I've signaled already, is have something more to say about how sensibility, that is our perceptual faculty, and understanding, our conceptual faculty, interact with one another in physics, so that they really need to be distinguished and then joined up together. So let me begin, as usual, with a quiz on who we are looking at. So we start with the easy ones. Yes? Cassirer, you're right, I slipped. Let's start with Kant. And this, of course, Kuhn. Now we know this is Cassirer. Okay, now the more difficult ones. Anyone know? Howard Stein, University of Chicago, Dean of Space-Time Theories. Even more difficult. George Smith, who teaches at Tufts. And I put Howard and George here. These are going to be the people who I'm most inspired by in doing the kind of history and philosophy of science I'm doing. Both of them emphasized the importance of relativity theory as a primary example, both Cassirer and Kuhn, and the history that led up to it, which is what I'm very interested in doing. I will give you some ideas why I'm not completely satisfied with what they do, although I couldn't have done anything I do without them. And I'll also say, out of needed humility, that in my own Dynamics of Reason, which is my earliest attempt to do a post-Kuhnian, neo-Kantian number, it's also all concepts and no perceptions, really. So I'm guilty too, and at the end I will explain to you why, if time permits. If time doesn't permit, I won't explain it. These two people are especially important because these, I take it, to be the two most important philosophical Newton scholars of our time, of the second half of the 20th century and the early part of the 21st. Both are alive still. Howard is alive too. And their emphasis on Newton is going to be a very important part of how I want to do this neo-Kantian thing. Okay. So let's first look a little bit about Cassirer and Kuhn. As I said, unfortunately, I'm going to say very little about them, but I'm going to indicate some things about them, basic ideas, and why I don't take them to be fully satisfactory. So Cassirer's Marburg neo-Kantianism is perhaps best represented by Substance and Function, Substanzbegriff and Funktionsbegriff, that was published in 1910. and then a work on Einstein's theory of relativity, which is about general relativity, in 1921. And he's defending this view that the Marburg School in general had, including his teacher Cohen, called the genetic conception of knowledge, which is emphasizing a historical evolution of knowledge as the key to understanding it, and trying to develop a kind of Kantian or neo-Kantian view within that. So let's just sketch the view as follows, that when we're talking about scientific theories, we're basically talking about mathematical structures that are described by sophisticated mathematical theories. It might be a spatial structure, it might be a space-time structure, it might be some other structure. Cassirer calls these things not structures, but systems of order. It's the same thing. So that's crucial, but you find those in mathematics too. So what's different about mathematics and science? Well, the history of science involves a certain kind of sequence of structures, which is different from any kind of sequence you would find in pure mathematics. And the crucial point is these structures do or should ideally converge over time to an infinitely distant limit structure. And that limit structure is going to represent the concrete empirical world as the completely determined individual object of experience equals X. It's like the thing in itself and the empirical world somehow coincide on this Marburg view. Okay? So what's the problem for that view? No adequate provision is made for the role of sense experience in articulating and testing theories. The empirical world only appears at the end of the story, not at the beginning or even in the middle. But at the end, we get the empirical world, and we certainly do not have a Kantian dichotomous balance between sensibility, that is our perceptual faculty. I don't necessarily mean pure intuition. That idea isn't a part of the neo-Kantian view that I'm articulating any more than it was for Cassirer, but I do want a perceptual faculty to have an independent status. And so there is no schematism of the understanding and sensibility, to use Kantian languages, in Cassirer. Indeed, the Marburg School deliberately says that the transcendental aesthetic should never have been written before the analytic. It really only makes sense after the transcendental analytic. It really should be subsumed under the understanding and not be separated the way Kant himself did. Okay. Now I'm going to talk a little bit about Kuhn, in particular his 1990 PSA presidential address, which was published in 1990 in the proceedings of the PSA, and that was called The Road Since Structure. And he goes through a very complicated discussion of what his view is. Darwin is really important. That's why this is post-Darwinian. At the very end, he wants to say, what kind of philosophical view is this? As opposed to just some kind of evolutionary epistemology of some sort. And he says, well, it really should be thought of as Kantian categories, which are based on what he calls a lexicon. I'll tell you a little bit more about that in a second. This lexicon supplies preconditions of possible experience, but lexical categories, unlike their Kantian forebears, can and do change, both with time and with the passage from one community to another. Okay. A little more detail. The lexical categories are fundamental natural kind terms, like gold and silver, or cat and dog. Those are examples he gives. Different sciences are delimited by different such categories. Now, this is after Kuhn left Princeton and he went to MIT, precisely so that he could use information about language, linguistics, and philosophy of language to explain better his notion of revolution and incommensurability and so on. Different sciences are delimited by different such categories. The development of the sciences involves a branching speciation process rather than linear convergence. There's no single thing that they're converging on. They're just developing and branching in a quasi-evolutionary way. And when you're at a branch point, that's where you get incommensurability, now really made very innocuous, if you think of it this way. Finally, at a branch point, there is theory change at every branch point, which Kuhn takes to be progressive, or most of the time progressive. And it depends on an increase in what he calls puzzle-solving capability, subject to a number of theoretical virtues or values. Okay, so to say what the problem is, I'm going to say a little bit more about what those values are. The theoretical virtues include empirical adequacy, successful prediction, but also non-empirical virtues such as simplicity, coherence, etc., which alone can reduce the underdetermination intrinsic to the hypothetico-deductive method. If all you have are predictions, the prediction is successful, you try to infer that the theory is correct, that's a very underdetermined inference. So people who think this way want to add these non-empirical values to narrow down the underdetermination. Well, I still think it's too much hypothetico-deductive method, and there's no place for Newtonian deduction from the phenomena. Not that we know exactly what that means, but Newton famously said, hypothesis non fingo, that is, he doesn't feign hypotheses, doesn't take a hypothesis to provide knowledge, and instead knowledge should flow from what he calls deduction from the phenomena, followed by being made general by induction. So the Newton is going to come in at this point. So another way to think of it is this. Kant's distinction between constitutive and regulative principles, which we talked about in the first lecture, or the first lecture and a half, if you want to call it that, distinguishing between constitutive and regulative principles. And the difference is that constitutive principles are necessarily instantiated in experience via spatio-temporal schemata. A schemata is something the imagination does when it mediates between understanding and sensibility. So for example, if you think of a triangle, and then you think about the construction of a triangle, and you imagine that, that is a very simple example of a schema for a mathematical concept. So here you clearly have a distinction between two faculties and a way to join them up. And then at this level, we get the metaphysical foundations of natural science, which realizes nature in general in space and time under this empirical concept of matter. And this is where you get proper natural science, and I mentioned several times in that lecture, Newtonian deduction from the phenomena is crucial to it. So what I want to do, I'm not going to start with the categories, the Kantian categories, nor am I going to start with the Kantian forms of intuition. Instead, I'm going to go down here when we're talking about theoretical science, and I'm talking about how theoretical science, which already involves empirical concepts, not just a priori ones, is linked still to perception by this kind of process. That's the key idea. So we don't necessarily have a priori forms of sensibility, but we do have a separate treatment of sensibility from the conceptual faculty and a systematic way of weaving them together, as it were, is what I'm looking for. Okay, so question. Is there a neo-Kantian version of the faculty of sensibility, that is, of the schematism of intellectual concepts and sensibility? Just what I've said. And I say, yes, there is. The notion of theory-mediated measurement, which is a way of linking quantitative theoretical concepts like mass, that's going to be my main example for a while, in terms of the way in which you measure mass. So the theoretical concept of mass is one thing. Then there are ways of measuring, because it's a quantitative concept, the value of that thing. We're not aiming to reduce it to purely observational sentences. It's not a reductionist program, but measurement gives us a link between perception and a theoretical concept which is quantitative. And then there's going to be a notion of phenomena that is appropriated to this notion of measurement. The phenomena is not going to be just what you can describe with observation predicates or observation sentences. It's going to include what you can do with quantitative theoretical concepts like mass, which are not observable directly, which are linked by measurement to observation. And then finally, there will be a version of scientific realism as a form of empirical realism connected to these other notions. So that's a kind of a setup. And so I'm going to begin this by talking a little bit about something Howard Stein did in 1989, a conference that was in Switzerland, Realism Today, in 1988. And this is a conference in which John Worrell first put forward the view of structural realism, and as he says, it's the best of both worlds, that is, realism and anti-realism, or realism and instrumentalism. Some people here have heard of this and know this view. Basically, what Worrell says is he's concerned about the objections to reference changing or disappearing in the history of science. He's worried about the so-called pessimistic meta-induction that theories in the past usually fail to refer or completely fail to refer. So how can there really be progress of a realist kind? And the idea is we forget about the reference, and instead we look at the structures that are being used to describe reality. So the example Worrell used famously is the ether, the luminiferous ether, the ether that is supposed to be the medium for light propagation, and the closely related electromagnetic ether, according to us, which mediates electromagnetic forces. Okay? And the idea is, and people usually say that, oh, when we get to Einstein, in some sense, there is no ether anymore, and that means that something would be wrong about these old theories. So what's that? Worrell says, still, even though the entity, the ether, isn't there to be referred to, still there are structural commonalities of the equations as we move from one theory to another, and that's enough to refute the pessimistic meta-induction, use the no miracles argument, and be a realist, but not a naive, reference-obsessed realist. Okay? So Howard Stein was at that same conference, and he wrote with a typically Steinian title, Yes, But, some skeptical remarks on realism and anti-realism, where he basically argues, without mentioning Worrell, that he doesn't accept Worrell's way of thinking about realism and instrumentalism. He also is not a fan of reference either, but it's a more radical view than Worrell's, so that's why I bring it up. And I'll tell you a little bit more about Howard now. Here's a quotation from Howard near the beginning. And I love it because he appeals to Kant. Because after all, Kant talks about phenomena. He wants to be talking about phenomena. First, there is the classical philosophical problem of the epistemology of transcendent metaphysics. The problem that Kant, we may say, posed to the ghost of Leibniz, and that led Kant himself to the view that all theoretical knowledge is of the phenomenal world. That is, the world of experience. The nub of the matter, he says, can be put very simply. How can you know that things are as you say they are if the claimed reference of the theory is something beyond its correctness and adequacy in representing the phenomena? If, as it were, it's talking about something behind the phenomena, then how in the world could we tell that it was correct or incorrect? That's what he's saying. Right. So if it's not about the world of experience, the phenomena, we're inevitably faced with skepticism, a very old form of argument. Now, you may be puzzled by this, and I was for many, many years, because isn't the idea that the phenomena is one thing and the reality another central to philosophy of science ever since Galileo? I think it was Nick Jardine who wrote a book called The Origin of History and Philosophy of Science. It was about the Galileo affair, and indeed this issue between these two folks, which is Galileo and Bellarmine. And what that's about is saving the phenomena. Bellarmine said to Galileo, if you would only say that the Copernican system is better for saving the phenomena that we observe from our position here on Earth, that's fine. Just don't say the Earth is really moving. Don't say that. It's just saving the phenomena. Okay, so that can't be what Howard means. Right? So what is the difference then between representing the phenomena correctly and adequately versus saving the phenomena? Well, one way one can begin to get a sense for that is that Galileo wasn't at all happy with saving the phenomena either. What he aimed to do is demonstrate the correctness of Copernicanism via mathematics and experience, not just take it to be a hypothesis or something that happens to fit what we observe. Rather, we should be able to prove from what we observe and the mathematical resources at our disposal that Copernicanism must be the right view. And for that, he had a theory of the tides. He tried all kinds of things. In truth, according to us, he never quite got it. But according to us, and all physics after Newton, he did get it. He succeeded in this task by determining the center of mass of the solar system. And here, the mass is going to be the theoretical concept. Basically, what Newton does is figure out a way of measuring the masses of primary bodies in the solar system that have satellites, such as the sun, which has the planets orbiting around it. The Earth has the moon, Jupiter has the moons of Jupiter, Saturn has the moons of Saturn. If you have Newton's theory of gravitation, you can actually infer the mass of the primary body from the acceleration of the satellite around the primary body. You don't just observe the acceleration either. You have to look at the period, you have to look at the distance, and so on. But it is something that you can determine from phenomena. And Newton takes it one step further via his concept of mass by, determining something called the center of mass, and then saying the center of mass is the true center of motions. And it always turns out to be very close to the center of the sun. The Copernican system is therefore almost perfectly true, but the sun is still wiggling a little bit due to the attraction of the Earth, but even more to Jupiter and Saturn. But it is the main source of mass, and therefore the center of mass is there. And so that's the center of motion. That's the only thing the true center of motion could mean. And we'll get to more of this in a moment. So that's intuitively the idea that if you're just doing saving the phenomena, you can't use a theoretical concept like mass as part of the phenomena. If you're doing this Newton thing, you can. But in other words, you mean by phenomena what is determinable by theory-mediated measurement in the right way, of course. Okay, so what I'm going to talk about now for a while is Newton's concept of mass. And it turns out that there's a number of different concepts that were in operation and were fairly well understood at the time, which Newton somehow weaves together in a completely new way. And I start with just three, but it turns out there's going to be a few more as well. And that's really the achievement of Newton making a measurable notion of mass which can work on near the surface of the Earth. It can work in the heavens. It can work anywhere you want to figure out the quantity of matter in a body anywhere in the universe, hopefully, if it's the right concept. So Newtonian inertial mass is a measure of resistance to change of motion subject to any force whatsoever, not necessarily gravity. That's the M in F equals ma. And that's Newton's invention. They didn't have this concept of mass before. It wasn't linked to quantity of matter. This is his concept. Quantity of matter was a vaguer concept, although it could be precisified in various ways. And what that's supposed to be is the amount of matter in a body. And the difference is that this concept has to do with the motion of the body and the possible response of the body to motion relative to various forces. This just has to do with the body itself sitting there, wherever it's sitting in the universe, independently of its motions, independently of forces. Just how much stuff is there? Well, that's not a very clear notion, but a popular notion at the time was there's such a thing as absolutely dense matter, with no pores in it, no interstices. It's as dense as it can be. In that case, the quantity of matter is proportional to the volume of that. Okay? So most bodies have interstitial vacuum on this view, and so it's the ratio to the total volume of the volume of dense matter. Perfectly precise, clear concept. Only problem is, how in the world would we measure that? I mean, can you tell me what the ratio is of this or that or any other thing? Nobody could do that. So it's a perfectly precise concept, but it doesn't aid any determination. Okay. Weight is also very familiar, and that's the tendency of bodies to fall towards the center of the Earth as measured in a balance. And this just comes from statics. This goes back to Archimedes and the theory of machines and all of that. And this existed way before Newton. It doesn't have to do with the theory of motion. It has to do with weight. And weight, the way we think of it here, is relative to the Earth, right? Because we talk about you can be heavier. If you were on the sun, God forbid, you'd be much heavier. If you're on the moon, you're lighter. And so mass is actually relative to the body that's actually the source of this tendency. But that's not true of either inertial mass or quantity of matter. Okay, so let's go with that. And here I'm going to start by talking about Kant and Newton on mass and quantity of matter, because I think that Kant actually understood these things about mass that I'm about to describe. Indeed, that's what helped me to come up with this way of dividing it up, which I think is the way Newton thought of it, but I think Kant did too. Okay, so I'm going to first begin with this quotation from the Dynamics of the Metaphysical Foundations. He's worrying about, of course, various people, mechanical philosophers especially, the people with those, the vacuum and the interstices, rejected any notion of attraction as an action at a distance. And here Kant is saying that, well, if Newton, because sometimes he's a little bit wary about it, to say the least, then he would actually be at variance with himself. I don't underline that here, though. When I first read this passage, I was obsessed with his difference with Newton. I wanted to say, Kant has something right that Newton doesn't understand. Well, that, I think, is not the right way to think of it. So instead, I'm just going to look at his example. What he wants to say is what Newton needs, and what he might not be able to say, is that the attractive forces of two planets, that is Jupiter and Saturn, for example, manifested at equal distances of their satellites, whose mass, by the way, is unknown, we can't measure those at that point, are proportional to the quantity of matter of these heavenly bodies, if he didn't assume that they attracted other matter, and so forth. Okay? But just let's look at what he's talking about with this attraction of the planets to their moons. So here I'm going to introduce the concept of acceleration field, which is also due to Howard Stein. And the idea is that a gravitational force has the property that we can, instead of just talking about the force on the body, we can forget about the mass of the body that is fallen, if you like, and just look at its acceleration. And one way to intuitively see this is what Galileo already showed when he mythically dropped from the Leaning Tower of Pisa cannonballs of radically different weights. Nevertheless, they fell with the same acceleration. So their mass, as it were, and their weight are irrelevant to the path that they actually follow, which is determined simply by their distance from the Earth and the properties of the Earth itself. Here we're kind of generalizing the Galileo property because we're putting in the inverse square law, according to which it's only at a given distance that they fall with the acceleration, but the inverse square tracks the way in which the acceleration decreases or increases the closer or further you are from the primary body. Okay? And then this constant here, which is a characteristic of the primary body, is really a measure of, if you like, the gravitational field strength of that body, as we would call it. Right? It's the power it has to attract a body at a given acceleration. Crucially, unlike every other force, you don't need to worry about the mass of the body that's being affected. Okay, well, I'll go through this a bit more. But given this acceleration field property, which I think is in Proposition 6 of Book 3 of the Principia, Newton goes on to deduce in Proposition 7 a way of showing that this field strength constant actually gives you the mass of the two attracting bodies, that is, of the primary bodies. Okay? It's a very simple calculation. I am going to have only very simple calculations. The only thing that's complicated here is the number of different overlapping concepts. Okay? So this is what you get already from the acceleration field property. And then the idea is, well, let's imagine that Jupiter is in the same acceleration field as Saturn's moons and vice versa. So we can extend that acceleration field from Saturn to Jupiter and from Jupiter back to Saturn. Okay? And then we have also the third law of motion, which says that the two accelerations of Jupiter and Saturn, respectively towards one another, obey this equality. So the accelerations are inversely as the masses. Okay? Well, then you put those two things together, and you get that the ratio between the mass of Saturn and the mass of Jupiter, this is now inertial mass because it comes from the laws of motion and the F equals ma formula. The ratio of these two field strengths is exactly the inverse of the ratio of these two. These two field strengths as these two masses. So that means you're actually measuring the inertial masses of the planets by the accelerations on their satellites. Okay? I will say this again a few other different ways. Now, but you can kind of see from this picture now how you figure out the center of mass of the solar system, right? Because this tells us the ratio between the mass of Saturn and the mass of Jupiter. The ratio. Okay. Well, Saturn and Jupiter are in the sun's acceleration field. They're falling toward the sun. Newton is assuming that we either have the Tychonic system or we have the Copernican Keplerian system, but the original Ptolemaic system is out because it's kinematically impossible that these things could not be orbiting the... Basically, you wouldn't get the second law, the area law, unless the planets are orbiting the sun. Also, the moons of Jupiter, the phases of Saturn and the phases of Mercury wouldn't come out right if they weren't orbiting the sun, E2. So there were several ways to think the sun's got to be the center of the planetary motion. That was, in a way, not controversial, at least not for Newton. And that's still neutral to whether the sun or the Earth is actually at rest. The sun has its moon. You can measure the sun's acceleration, say, by Venus, something that's neutral here. We know the ratio of Saturn and Jupiter. Then we can know the relation between Saturn and the sun's mass, Jupiter and the sun's mass. No surprise, the sun's mass is much bigger. What about the Earth's mass? Well, we can just use the Earth moon to do that. Easier said than done. And now we can compare the wall. The Earth has very tiny mass. Jupiter and Saturn have pretty good mass. Sun's got a lot more. If you line up all the planets on one side, the sun on the other, the center of mass is still going to be within the body of the sun. Okay. So that's how that argument gets. And that's what it means to measure or determine by empirical measurements of this concept of mass to determine the true motions. So it's a piece of physics, as it were. It's not a piece of metaphysics. Okay. Now I'm going to look at the acceleration field property in a slightly different way to make it a little clearer, perhaps. And that's to connect it to the full law of gravitation that the force of gravity between any two masses, m1 and m2, are directly proportional to the product of m1 and m2 and inversely proportional to the square of the distance, right? No ma, though, yet, right? So this is what we call gravitational mass. Mass as the source of the gravitational force. Right? So it's not inertial mass yet by itself. It's not quantity of matter. It's the source of the gravitational field, so it would be something like that constant. But we're going to show, and it'll turn out, because of everything I've said so far, that it just is mass, inertial mass. And now we have gravitational and inertial mass put together, right? So this is the FMA, F equals ma, applied to this mass m2. This is the force applied to m2. And so this is the inertial mass, but the idea is these things are equal. That's one way to think of this. And so they cancel out, and this doesn't figure in the fall of the body or its acceleration. And so gravitational mass is the source of gravitational force, but inertial mass is there independently of gravity. It turns out they're the same. Why? Because of the acceleration field property. Or because this is true, you have the acceleration field property. Now we're going to multiply the masses even more. But from the equality of these two, we get this, that the acceleration of m2 towards m1 doesn't involve m2, but just the mass of m1. Now I've put our constant g, which wasn't there for Newton. It was always proportionality. But to make it easier for us to understand it, and of course it's here already, it's a universal constant. And so this is a way of measuring the mass. Now, to make things a little more complicated, we can distinguish between passive and active gravitational mass. Right? Now, in this example, the passive gravitational mass is m2, and the active one is the mass of m1 because it's doing the attracting, and that's what we can measure. Now, you might wonder, well, aren't they both equally passive and active because the two bodies are attracting each other, right? Well, but we can't measure. We can't measure, at least at this point, the acceleration produced on, say, the Earth by the attraction of the moon. But we can measure, assuming the orbit of the moon, and therefore we can measure its acceleration. So relative to what we can measure, we go for the orbit of the moon, we get its acceleration, and we infer from that the mass of the source of the field. Even though we know the moon also attracts the Earth a little bit, eventually we want to incorporate that, but at this point we don't know how to measure that thing at all. Okay? So this would be the panoply of different masses, aside from the three I started with. Okay? And the crucial point is, in terms of this language, it's active gravitational mass relative to some orbital body that enables measurement of quantity of matter, of primary body, the acceleration of satellite. So far, so okay? Good enough? Anybody want to ask a little question at this point? Yes, please.
I always was bothered by Galileo's experiment, and I read that the reason it works is because inertial mass counteracts gravitational mass. Is that
Well,
can I get that from this?
well, yeah, it's because inertial mass is proportional to the passive gravitational mass of the body that's attracted. It's a version of a principle of equivalence, a Newtonian Galilean version, not the relativistic version. But it's the same idea. This was already known to Galileo and Newton, and indeed they couldn't make their arguments without it. Okay, so I will go on. Now let's look at the moon a little bit more closely. Oh, no, sorry. First I have to look at weight. So now we're going to just look at ordinary weight in statics. This is very simple. There'll be a few equations, but the crucial point again is are the concepts. So we got these two things here, two bodies, and let's suppose that they are in equilibrium here on this left and right balance with equal arms. So the weight of this is equal to the weight of that, kind of by how this is set up. Fine. So what does this have to do with the different kinds of mass that Newton introduces? Well, here's inertial mass, and according to Newton, this weight is actually due to the force of gravity of the Earth as it is pulling these things toward the center of the Earth. So it's the force, it's the gravitational force on each of the bodies, from Newton's point of view, is just what the weight is. Okay? Now, so how do we get this inertial mass to come in? Well, by the Galilean property, these accelerations are equal near the surface of the Earth. Right? That's a given. Well, therefore, the inertial masses are equal if the weights are equal. So let's look at this again with some color. Let this thing be the concept of weight, and let this thing be the concept of quantity of matter. It's just, the amount of matter that's there, whether it's on a balance, whether it's on the moon, whether it's in the sun, whether it's just floating off in space. There's some kind of amount of matter there as an invariant property, and we want to be getting a handle on that too. How do we do it? Well, if we're Newton, we get it through inertial mass, because inertial mass is also an invariant property. It doesn't depend on where the thing is near. It's defined relative to any force whatsoever, and it's just a measure of the resistance that body can put up. And so if we use that as an indication of the quantity of matter, which Newton does, and he has various reasons for it, and various experiments he brings in, it never ends. We don't have time to do that. And that's how these things are then all linked from a Newtonian point of view. So now the crucial thing is, how do we connect weight on the surface of the Earth with what's going on in the heavens? Well, that involves connecting the moon to the falling bodies near the surface of the Earth, the so-called moon test. So we start, never mind for the moment how we know this, that like the other planets in their orbital motions, there's going to be this kind of inverse square law, and this is going to be the gravitational field strength of the Earth. We have to say how we know that, and I'll wait and do that in a moment. And then we've got this acceleration toward the center of the Earth. R is this whole radius here. Now let's imagine that the moon comes down to the surface of the Earth, or at least we imagine it getting down there. So then it's going to be at the distance d rather than the distance r from the center of the Earth, and we then use the inverse square law to bring this thing down by using this formula. And this, Newton shows, is actually numerically the same as g, the gravitational constant of Galileo, 32 feet per second of acceleration. Okay? So if we've got the Galilean constant, if we've got this inverse square thing for the Earth, for the moon, then it turns out the moon can be viewed as a falling body in what you might call a quasi-Galilean field. It's not constant everywhere, but for Galileo it's just constant because he's considering bodies that are just very close to the center of the Earth. But if you consider bodies at any appreciable distance and you have Newton's inverse square law, then of course it's going to get weaker the further you get. But it's still at any given distance the same for any body, regardless of its mass. Okay? And so then if you now just look at ordinary bodies near the surface of the Earth, their weight is going to be this also, and their acceleration is going to satisfy this, and again, it's going to equal g. So this moon test makes a connection between the celestial treatment of gravity and the ordinary terrestrial gravity, already pretty much figured out by Galileo. So when people talk about the apple falling on Newton's head, what they mean, he was imagining the moon falling on his head, and that's how he got there. Okay. But of course, he had to do all these measurements to corroborate it. Now, it's a little more complicated, but it makes it more interesting, too, if we now ask, how do we figure out that the moon obeys that law? Now, in the case of a body that has a number of different satellites, like the Sun, like Jupiter, like Saturn, the way you derive that acceleration field doesn't just hold within one orbit, that is the inverse square property, but it actually holds from orbit to orbit as you get further away. That follows from Kepler's third law. And that's how it's inferred for the planets relative to the moon, for the moons of Jupiter relative to Jupiter, and similarly Saturn relative to Saturn. But all we got is one moon here. And furthermore, the moon is pretty ugly in its motions, which Newton is indicating already. So the first thing he says is in the phenomena where he's going to make his inferences from in book 3, the crucial phenomena for the moon is that the moon, by a radius drawn to the center of the Earth, describes areas proportional to the times. Actually, the motion of the moon is somewhat perturbed by the force of the sun. But in these phenomena, I pay no attention to minute errors that are negligible. So why are you telling us about it? He doesn't actually mean that. Proposition 3, which is now a theorem, the force by which the moon is maintained in its orbit is directed towards the Earth, that's going to follow from this, and is inversely as the square of the distances of the places from the center of the Earth. That's now a stronger thing to say. The second part, he says, is evident from the very slow motion of the moon's apogee. That is, the way the moon progresses from its furthest point to its nearest point in its orbit is a very, 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 very slow precession. But there is a precession. And Newton has a theorem that says if it's completely stable, it's exactly r squared. Well, it's not exactly r squared. The exponent is a little bit greater than r squared, and Newton calculates that as like 1 over 254 or some ridiculous thing like that. And then Newton says this motion of the apogee arises from the action of the sun, as will be pointed out below, and accordingly is to be ignored here. Well, why are you telling us that? Well, the truth is, this is really a promissory note that Newton is making. He's saying, I'm going to show you eventually, I hope, that it does all arise from the attraction of the sun. And if you're just doing the Earth, inverse square is there, you add the sun, you get exactly the difference you want, you're fine. Later in book 3, in the very hard parts of book 3, he attacks the three-body problem. He tries to figure this thing out. He tries to prove that the sun is exactly adequate for this 1 over 256, whatever it is. It doesn't quite get there. And this is the one place where Newton famously said, I just got really bad headaches whenever I thought about the motion of the moon.
Didn't he have an argument with Flamsteed or some astronomer royal about his measurements? Didn't he have a problem with
There was some stuff with Flamsteed that had to do, if I'm remembering correctly, the question Flamsteed asked Newton was, well, how come the moons of Jupiter and Saturn are so well behaved? Because they don't have any funny thing going on. Of course, the sun is affecting all of them, but by corollary 6 to the laws of motion, it's all falling toward the sun along nearly parallel lines, and it's pretty constant. Furthermore, it's so far from the sun that the sun is relatively weak compared to the acceleration of Jupiter and Saturn, so that the perturbations that are actually there are so small that we can ignore them. Not so for the moon. That's why the moon is different. It's close, very close to the sun and the Earth. There's no parallel lines there. And furthermore, there's a great big mass sitting off there, very near the Earth, which is making a definite contribution. Fortunately, it's still small enough that Newton can say with good conscience that most of it is due to the Earth after all. There's just this little 1/256. And of course, you know the story. Some people thought maybe that exponent has to be changed. It was very hard to get this figured out. And actually, after Newton died, it wasn't figured out until the 1740s by Euler and Clairaut, when they finally showed, yes, if we do it right and we look at the sun's contribution, we look at the distances, we look at the Earth's contribution, actually it turns out that that accounts for the whole thing. Clairaut had earlier thought that the exponent should be changed. So that was in 1740, so it was much later than Newton. That shows you that Newton was making an approximation that he tried to redeem, but it wasn't truly redeemed until later. Okay? Now, this kind of thing, this incorporation of perturbations into the theory of gravitation, Newton also began doing that with the perturbations between Jupiter and Saturn, the so-called great inequality, but he didn't get as far as people got later. But the same thing is going to hold for Kepler's laws, right? Kepler's laws relative to the sun, say, where we pretty much ignore that they're attracting the sun too, and we certainly ignore that they're attracting each other, that is the different planets. We just treat them as following what Kepler said. Well, that's not exactly right, because they are attracting each other if Newton is right about universal gravitation. So that has to be brought in later, and it is brought in later. And then we see that Kepler's laws as written are merely approximations. They're pretty good ones, but the approximation is explained and redeemed so that nothing but gravity explains it later on. This whole thing ended up being quite successful. The most spectacular example was the discovery of Neptune by Adams and Leverrier in 1846, where the perturbations on the orbit of Uranus had various funny things going on. People said, well, maybe there's a planet beyond there which is attracting it, and if there is, this is where it should be, and this is what its mass should be. You know, and lo and behold, they looked with the telescope, and there was Neptune, just what the doctor ordered. This is a spectacular success of Newton's theory. So everything was going along fantastically well until it got to the perihelion of Mercury, where there are perturbations. It's very close to the sun, and the other inner planets too have them. And the sun's gravity isn't enough, nor are any other perturbations that are visible enough. They tried, postulating the planet Vulcan that would be closer to the sun or something. They couldn't do it. They just couldn't. Very, very tiny advance of the perihelion. There's no way you would even know about it if you didn't have Newton's theory to tell you it was there. And again, we know that it was only Einstein's general relativity that got that figured out, which changed the whole theory to a variable curvature in the fabric of space-time rather than a Newtonian force, 1915. But all of this worked amazingly well. Eventually, it did give way, and the law of gravitation had to be changed as well. And of course, we're going to talk about that. Okay. Let me go. I think I have time to go a little bit further because I haven't even gone an hour yet. I've gone almost 45 minutes, but let me go a little further. Let me now talk about this further thing that I was indicating, the Newtonian style. This idea was originated by I.B. Cohen in the Newtonian Revolution, 1980, where he says, well, it's characteristic of Newton that he starts with a highly idealized one-body system, just a point that has an orbit around it. If you have that, you have exactly Kepler's laws. If you have a two-body system, there's a correction because of the mutual attraction of the body that is satellite with the central body. And when you get to three and many-body systems, then you get all kinds of perturbations. But what Newton is always doing is adding further sources of gravity which still obey the law of universal gravitation. So until you get to the Mercury problem, he is able to do that. by having more and more sophisticated, or he was, or people were, perturbational methods, telescopic observations, still using the Newtonian law of universal gravitation. So this sequence of successive approximative corrections is essential to Newton's method. We don't get the final true thing, but we're able to get better and better corrections to what we said before. So that's part of what Newton means by deduction from the phenomena. And George Smith, who worked with I.B. Cohen, edited the Cambridge Companion added the notion of theory-mediated measurement to Cohen's idea of successive corrections based on idealization, which turned out to be very important. So I've gone a little more than 45 minutes. So I suggest that to give you a little bit of a break before I turn to some more things about Kant and Newton and then eventually to Einstein, why don't we take a 10-minute break, and people should feel free to ask me some questions that may have come up already so far, and then I will go on. So we're going to kind of divide the question period up into some different units like we did last week. Now we can start. So now I'm going to talk about, I'll just show you this picture, which I've shown you before, which is the essential beginning of this method of successive corrections. Propositions 1 to 2 of Book 1, where properties of the force that is, the centripetal force that is producing this orbit are related to the motions in the orbit itself. Okay? So this is a very basic example of theory-mediated measurement. And one thing about this is that the notion of force is a rather abstract one. Right? It's just whatever it is that is producing this motion towards the center, that has this relation to the inertial, tangential motions that would be there if the force weren't acting. We don't need to know anything about what kind of force it is, what its mechanism is, just that it has these properties. That's sufficient to do these deductions. Okay. So I say Kant accepts Newton's abstract treatment of impressed force as a measurable mathematical magnitude considered independently of any hypotheses concerning underlying mechanisms. And what I mean by abstract is not, of course, that it's an abstract mathematical entity. No, it is a physical, theoretical quantity, that is force. And we abstract from, though, further explanations of how that force is working. That's the abstraction. Until we have a way of measuring what that might be. Okay? And I'm going to, here's some things Newton says very famously. This is the hypothesis non fingo. I'm not going to read it out because time is going on. But he mentions propositions are deduced from the phenomena, made general by induction, so that's a crucial part of the abstraction from hypotheses. And finally, it is enough that gravity really exists, and there are these laws regardless of what is actually causing gravity to do what it does. And he's open to the idea that there is something doing that, but we don't know that yet, so he proceeds this way. Here's the passage from Kant, and I just want to emphasize here is he's saying about Newton that Newton rightly abstracted from all hypotheses, purporting to answer the question as to the cause of the universal attraction of matter. For this question is physical or metaphysical, but not mathematical. And he's suggesting that at this point, Newton is right in taking this mathematical point of view. So that's why I emphasized the rightly, which I hadn't emphasized before when I was saying this was a difference between Kant and Newton. There is a difference there, but it's not as deep as I thought, I think. We can talk about that if everybody wants to. So again, Kant accepts this abstract treatment of impressed force as a measurable mathematical quantity. And once we've got that, we must then show, and we can show, that gravitational force in particular has the mathematical properties required in order to facilitate theory-mediated measurements of both the force itself, like its inverse square properties, and other centrally important related quantities. For example, time. This is how we can measure time on the basis of this law. Because there are no bodies that are just moving perfectly inertially in this world of Newton, but there are bodies that are orbiting, and we can use the law of inertia and Euclidean geometry that the force acts equally between B, C, D, E, and F, always directed toward the center. Then the areas of these triangles are going to be equal, so we can use those areas as measures of elapsed time. Furthermore, prominent among these quantities is quantity of matter, the measurement of which in the theory of universal gravitation involves a direct application of actions and reaction, conservation of momentum, between arbitrarily distant bodies. In that sense, there's some kind of commitment to at least momentum conservation at a distance by Newton. That was the point Kant was really emphasizing. This kind of abstract structural conception is not a version of Worrellian contemporary structural realism. Now, that's the point of what Stein is saying, because he's not a realist in that sense. Stein wants to say that both realism and instrumentalism are basically right. It's only anti-realism that's bad. What is instrumentalism? It's the emphasis on the experimental measurements that you need to have in order to be licensed in ascribing to the phenomena the theoretical concepts that you want to predicate of them. It rather concerns, in my view, the methodological use of theory-mated measurements in ongoing inferences that are more secure than either inductive curve-fitting or hypothetico-deductive arguments. This is the George Smith idea. And again, the idea of the greater security is that Newton can settle as an empirical matter within physics by measuring the way he does quantities of matter in the solar system. The issue between Galileo and Bellarmine, it's no longer a theological or metaphysical issue. What Galileo said was right, he just didn't know how to prove it, and Newton is now demonstrating it. And ever since Newton, at least in physics, it's accepted that that is the answer to the world question, world systems problem. This is just in a way a throwaway, but I think it's important that Kant, of course, has an anti-Humean conception of causal necessity. This came up also last Wednesday in conversations with Mike Strevens, not Mike Strevens. Yes, Michael Strevens. And what I'm saying is that this is a centrally important constituent of that anti-Humean conception. That is, this greater security of inference, and so at bottom it's an epistemic notion of necessity for Kant. These inferences are subject to later refinements along new and unanticipated dimensions that may become clear only post hoc, that is, after you've made them. Those are the sequence of corrections and approximative improvements. Finally, Kant is less explicit about, and in the end less open to, such refinements than is Newton, but hold on a moment. Here in the appendix to the dialectic on the regulative use of reason in both the first and the second edition of the Critique, he's talking about the orbits of the planetary bodies and how we arrive at the unity of their cause, i.e. gravitation. From there, we afterwards extend our conquest further, seeking also to explain all variations and apparent deviations from these rules from the same principle. If those aren't the planetary perturbations, I will eat my hat. Kant mentions them here. It's the only place that I know of that he does. So he's completely open to all the corrections that can be made within Newtonian perturbation methods. Where he's not open to is general relativity, where you've got curved space-time instead. This is not something Kant can accept because space is an a priori form of intuition, and it is Euclidean. Damn it. So there's no room for gravity to be explained that way for Kant. But all the Newtonian stuff is good. So I put here, the Newtonian explanation breaks down, however, in the case of the period of Mercury, then replaced by the Einsteinian explanation, which essentially involves a non-Euclidean spatial as well as spatio-temporal geometry. So now we finally get to this. However, to talk about general relativity, we have to first talk about electromagnetism and special relativity, because without those, you would never have general relativity. And so it's only because we've got a new fundamental force in the 19th century being articulated and rigorously characterized throughout the 19th century, perfected, we think, by Maxwell. The second of what we take to be the four fundamental forces of nature, to describe it anachronistically. First, gravitation, second, electromagnetism, and then the strong force, the weak force, etc. Okay? But we don't go there today. We just go through electromagnetism and Einstein. So first, let's talk about Maxwell and the electromagnetic field. It is an abstract measurable magnitude like Newtonian gravitational force. Unlike the latter, however, this field of force is itself dynamical, perhaps not the happiest idea, but what it means is it is propagated through space with a definite finite velocity. It is thus an actor in the physical world. It exchanges momentum with other things. Just like in the Newtonian world, the massive bodies exchange momentum, but the gravitational field is just an instantaneous, if you like, static thing, and so it isn't an actor in this sense. But the electromagnetic field is, and that's connected with its finite speed of propagation. Stein, 1970, I don't mention it, I don't give you the, but that's an essay by Stein called On the Concept of a Field from Newton to Maxwell and Beyond. He barely gets actually to Maxwell, because he goes on and on about Newton for a long time, but he does get to Maxwell and says interesting and provocative things. That's the paper I'm referring to here. Okay, but how do we know this? How do we know that the electromagnetic field satisfies Maxwell's field? So we have to back up a little bit. So let's go back to the phenomena that started our knowledge of electromagnetism. First, Ørsted's discovery of electromagnetism, that is the electric current, produces a magnetic field, and it satisfies this right-hand rule. Okay? Second, that was around 1820. This is, I guess, around 1828, if I'm not wrong. Faraday shows a kind of inverse thing where you can, if you have a moving magnetic field created by these, in this case, electromagnets, that's going to create a current here in this coil, and that will be measurable here. So a current, which is some kind of movement of electricity, produces a magnetic field, and a changing magnetic field produces a current. So these are just phenomena that were discovered. Okay, well, so how do we go further? Well, the decisive thing, which happens quite a bit later, is Hertz's experiments with electromagnetic waves, and indeed radio waves, which establish what I'm going to call the structural properties of the electromagnetic field, that is, those abstract field theoretic things, via theory-made measurements, just as the corresponding properties of gravitational force were similarly established by Newton's deductions from the phenomena. Hertz thereby experimentally established in particular the Maxwellian displacement current. That comes from Stein. Maybe I'll have a chance to tell you something more about that. But now, how did Hertz get to this experiment, and how did we get to this point? So let's look a little bit back with Helmholtz. You might remember that Helmholtz was important in the development of electromagnetism in the 19th century, and he thought that these Kantian action at a distance forces in the Newtonian style, either repulsive or attractive, were sufficient to handle all of this stuff. So he took the metaphysical foundations of natural science as basically right about force, and he thought it was also right about all the forces of nature, at least when he started. And in this, the conservation of force memoir, especially in the first edition of 1847, his argument was that these kinds of forces suffice for everything in electricity and magnetism and electrochemistry, and he was pretty happy to speculate or give arguments for them also carrying over into biology. But we have enough trouble with electricity. Okay. So let's now look briefly at the development of electrodynamics in the 19th century. In the 1820s, we have early reactions to Ørsted, especially Ampere, who gave a more detailed law for the creation of the magnetic field by a steady current. And Ampere talked about forces exerted by electricity in motion. And the idea was, at the bottom are going to be some kind of particles, charged particles or something like that. And those can be moving or they cannot be moving. And when they're moving, we're talking about electrodynamics rather than electrostatics. And so what's really going on there is there's something, I mean, what we would say is there are electrons flowing through there, and those are exerting forces on the magnet and so forth. The magnet, in turn, gets its magnetic properties by its microstructure, which consists of maybe little rotating atom-like things where the charges are all lined up the way they're supposed to be when you have a magnet. And you have an interaction between those forces in motion and the forces in the wire that are in motion. And actually, using action distance forces, you can get pretty far. Works pretty well. Okay. So Ampere did that. In the 1840s in Germany, Weber had a mechanical action distance approach in Germany, very much indebted to Ampere. And Helmholtz, in the first edition of the Conservation of Force, just adopts that. For him, electrodynamics means Weber. So, of course, it can all be reduced to a Kantian or Newtonian action at distance framework. Between 1850 and 1880, Maxwell's elaboration of Faraday's field theoretic approach, well, was elaborated, and it also began to become known on the continent. Helmholtz reacts in the second edition of his monograph, 1881, with formulations. It's not that he adopts Maxwell. What he tries to do is be neutral. He says, well, let's just have an action potential between macroscopic bodies. And let's try to set it up so that that action potential will give the same kind of interactions between macroscopic bodies, like wires and magnets, that on the one hand, the Ampere theory or the Weber theory gives you, on the other hand, what the Maxwell theory gives you. So it's supposed to be neutral. Following Helmholtz, Hertz in 1884, he was a student of Helmholtz, attempts to show that the field theoretic approach of Maxwell and the mechanical approaches are actually equivalent, that you're going to get the same results in all of those, both of them. However, he soon encounters insurmountable obstacles proving that they're equivalent, and he finally realizes that only Maxwell can give you continuous and finite propagation of electromagnetic action, which you're not going to get in that action at distance theory, no matter what you do to it. Okay? So then he says, well, what I got to do now is show that there really is this propagation. Of course, it's pretty fast, the speed of light, so this is easier said than done. But he attempts experimentally to demonstrate the existence of this propagation, and that's what he succeeds in doing in 1688 with radio waves. Right? Basically, he's made a little, there's an induction coil. We get signals, radio signals being, they have very long wavelengths, so you know, in like 6 feet or something, you get one cycle. And then there's something like an antenna that picks it up, and then there's a current flowing through that wire, and that's going to match the frequencies in the original current, the original wires, but it's going to have a time lag of C between its reception and what was going on in the other one. And that's basically how our cell phones work. Okay. Although, of course, the microwaves are a little shorter than the radio waves, but that's basically how it works. And this is how we live with this fact. The longer wavelengths, the shorter wavelengths, and here's the visible part of the spectrum, so that light is subsumed. But what's so important is not just that light is unified with electromagnetism. That's a relatively trivial thing. The point is, even if you're just worried about electromagnetism and its laws, the Maxwell one is the only one that gives you all the effects that you observe, including the famous displacement current, which is a correction that Maxwell added to Ampere's law of electromagnetism. So it's not just a steady current, but a changing electric field too is going to give rise to a magnetic field. All right. So enough of that. Yeah. Okay. Question.
Did ether come about from the mechanical version of E&M?
Scholars say that the displacement current first came into Maxwell's mind as a feature of one of his ether-like models. So he put it in. Because after all, how did he know that that was there? It wasn't until Hertz that we actually could show that it was there. And Maxwell eventually is less concerned with the mechanical models, and he's more concerned with the properties that those models all have in common. And he turns to analytical mechanics rather than an ether reduction program. Okay. So there we are. Now, once we've got Maxwell with its finitary production at the velocity of light, we've then got a problem in putting Maxwell and Newtonian gravity together. Newtonian gravity propagates instantaneously at a distance, supposedly. Okay? So what is this picture a picture of? I didn't say much about it, unfortunately, last time. This is an event happening at a certain time. Let's imagine that you light a match at this time, and over time the light spreads out uniformly around the match, and you get this cone over time of an expanding sphere of light. Okay? And this plane S are all the events that are simultaneous with this one. And similarly, if you've got one up here, it's all the events that are simultaneous with this one. And the idea in the Newtonian theory is that, somehow a tacit idea, is that there's only one, given an event, there's only one plane of simultaneity that it's on. Right? So it's an absolute thing. The plane of absolute simultaneity is an invariant structure in the theory. Not only is the light cone an invariant structure, but so is the plane of absolute simultaneity. Why? Because Newtonian gravity is instantaneous. But these two structures are compatible because then you can't get light having velocity, the same velocity in different inertial frames, if it has this Galilean structure. So something's got to go. And what goes, as we now think, this is somewhat anachronistic, according to Einstein-Minkowski, is that the relativity of simultaneity has to be introduced in this geometric way, where when you get to an inertial frame moving with a certain velocity relative to the original one, then the plane of simultaneity, the simultaneity relative to this thing, has got to be tilted accordingly. And if you do that, you can see that, well, these ratios can actually be equal. It's the only way they can be equal. So these are the two pictures from my Foundations of Space-Time Theory book, and I hope this doesn't provoke Tim to now disown entirely the book. Okay. So what we take to have happened is that we went with Einstein-Minkowski at this point. It's not to say you never are going to find a reason to have absolute simultaneity again. Maybe collapse and all that is going to make you do that. But at this point, we don't. At this point, we've got electromagnetism, we've got gravitation, but now we need a new theory of gravitation because we don't have the Newtonian action at a distance instantaneous theory. So the space-time itself is Lorentz invariant. The structural properties of Maxwellian finitely propagated causality are also those of the new spatio-temporal background structure, namely Minkowski space-time. As I say, this is anachronistic. Einstein didn't even accept Minkowski until much later. Well, until like at least maybe 1912, but certainly in 1908 or 9, he didn't accept it. He thought it was a superfluous mathematical twiddle. It obscured what was going on. But later, of course, with general relativity, he bought it. Okay, the Michelson-Morley experiment, one can think of as establishing this structure in that it shows that the velocity of light is indeed the same, as far as we can tell here. The idea is this thing is rotating. It's mounted securely on the Earth, as securely as one can mount it. The motion of the Earth should have some effect on the velocity of light. And that's why this interferometer sends it out in different signals, but it rotates. So sometimes it's perpendicular to the motion, sometimes it's parallel to the motion, but never do you get any interference fringe indicating that there's any motion at all. So we conclude that you cannot determine the velocity of light this way, okay, as a Newtonian kind of thing. All right. And then general relativity makes it essential to bring in the light cone four-dimensional Minkowskian structure, but now is something that can be perturbed by gravity to have space-time curvature, which is indicated in this nice diagram from Gauroche, general relativity from A to B, which shows a black hole, which is a much heavier version of what the sun does, but it's a similar kind of thing. And it's the tilting of the light cones that is causing these bending of light near the thing and then entrapment of light within the black hole. And here's how the three-dimensional spatial geometry looks more intuitively. But as they point out in the diagram here, Actual travel takes place in space-time rather than space. Correct deflection is twice that given by this above elementary picture, and that means you have to use this rather than this to get the whole story right. But this is a very intuitive story. And of course, there is spatial curvature there. It's just not sufficient. Okay. So I think I could just plow ahead for a little bit more. So here's the attest in 1919 of these eclipse predictions of the bending of light. There's an eclipse path going from Africa here to Brazil. And this is the one in Brazil, Sobral. And there was one in Africa too. There were two different expositions, one here, one here. Eddington was in one place, someone else was in another place. Here's the observatory in Brazil. These are large astronomical cameras. They don't necessarily work perfectly, but they're there for redundancy purposes. And the important thing to know here is that this was a test of Einstein's prediction for the deflection against an already existing Newtonian prediction of the deflection. What kind of Newtonian prediction? Well, imagine you're a Newtonian, you have a particle theory of light, just very small mass, it's very fast. And let's imagine that you have a sun or a star with a big gravitational field. Well, that thing is going to be attracted, and it indeed could be trapped by that gravitational field. So there can be black holes, there can be deflection if you have a Newtonian theory. It's just that that's about 1/2 the amount that Einstein predicts. And when they look carefully, Einstein is pronounced to be the right number. Okay? So it's being established relative to the Newtonian prediction, which you can jigger up a perfectly reasonable Newtonian prediction for how light is affected by gravitation in the way I suggested. And that was fairly well known, and Einstein was certainly they were working with that as a point of comparison. Okay, now I say something here which there may or may not be time to go into further. Kant and Einstein. Well, what I say is something kind of intuitive, but not really sufficient. What I say is, well, look, if you look into the dimensions of this little observatory here, maybe it's 10 cubic meters, maybe it's 20 cubic meters. It's not very big. If you look at the length of this light ray, well, it's about 150 light years from here to these Cepheid stars that are being in the picture. So even though there's curvature in the large, there isn't curvature down here in the small. So we can kind of take this not to have curvature. I say that's kind of okay as far as it goes, but it isn't really sufficient. And if there's time later, I can talk a little bit about that.
Sufficient for what?
For understanding the relationship between what's going on in the observatory and what's going on, or what can go on. Well, basically, here, there's a really simple answer, actually. This is probing the gravitational field of the sun. That's all we care about here. The gravity of the Earth has nothing to do with this. Similarly with Mercury, it's the gravitational field of the sun. The Earth has a gravitational field. Otherwise, we would be floating off into space, right? So there is a gravitational field here, and therefore there's space-time curvature there. And it is possible to determine it with other experiments, and in particular with gravitational redshift experiments. And if anybody, at the end, I will say something about that if there's still any time or interest. Okay? So the relationship between the space of the observatory and the space of the cosmos is a more subtle and complicated one, which has to be figured out. Okay. So now I'm going to get to the Kantian legacy. So this is good because I'm going to stop at some finite point. Is there a neo-Kantian version of the faculty of sensibility of this? Yes, there is. This notion of theory-mated measurement as modeled on the Newtonian method and the Newtonian style seems to be a really good candidate for that. And that gives you a notion of phenomena that is in a sense theory-laden, but still measurable, determinable through measurements that we can carry out in the real world that we live in and see. And there is a version of scientific realism connected to empirical realism here. We saw that in Stein. We also saw that I'm going to come back to this even again. So I think at least I've made a gesture. I've said quite a bit about the quantitative theoretical concept of mass. I've gone faster over other things, but the mass is a good example, I think, because that's very typical of what Newton does. It's an amazing conceptual achievement, really. And we saw from Stein that there is a notion of phenomena that makes that idea central, so that it's not just something reducible to observational predicates, if you like. And there's a version of scientific realism in Stein's sense as a form of empirical realism. Okay. I also had these points up, and here the crucial point is that these inferences get their greater security. This is the force of the deduction from the phenomena. It's, of course, not really deduction from the phenomena. Otherwise, from our observations of the planets, we could deduce, first of all, Kepler's laws, and then we could deduce the law of universal gravitation. But you can't deduce Kepler's laws because they actually aren't exactly true in the phenomena, because there are perturbations. So get real. What it means is that there is a procedure of starting with quite good approximations that almost follow from what you perceive within margins of perceptible error. Then you find ways of making them more precise by taking into account of further gravitational forces, still gravitational forces. There's a sense in which Newton is amazingly lucky to be given the solar system to work with, because on the one hand, there's only one force, essentially, that matters, gravity. And he has found a law for that that seems to work, damn well for hundreds of years. But it's still complicated enough because all the perturbations, all of them except when we get to the end, are due to other gravitational forces without changing the gravity law. So that's a very fortunate situation where no wonder this method worked for so long. Right? There's an element of contingency and luck to that happening, but fortunately that's how it happened. Here I want to focus on this. These inferences are subject to later refinements along new and unanticipated dimensions, velocities, energy scales, size, distance, you name it. The later refinements are always open in this method. Even where we give up Newtonian forces entirely and instead for gravity use four-dimensional space-time curvature. That's a radical change conceptually, but it comes smoothly along in terms of the increasing accuracy of the approximations that are being revised. It's just that we couldn't anticipate that the way to fix the Mercury problem was that. Einstein got to that, but it's not something that we somehow was just sitting there for us to already know. Okay? So from that, I want to make a little bit more radical claim that's going to ire many people in this room. There is, and then I'm a little gentler here, or at least maybe, no ultimate fundamental level of physical description. Why? Because we're always looking at a certain scale and a certain dimension of things that we can theoretically describe, but more importantly, measure with the equipment and capabilities that we now have. Right? So, and what's going to happen when we get that capability, we can't anticipate from where we are. We can guess, we can hope, we can postulate as a regulative ideal, but we can't know. And so far, we've been surprised every time this happens. Something got introduced that we just couldn't imagine before. Okay? So this is my suggestion of a non-fundamental realism, if you like. A non-carving nature at its joints type of realism, but it's still at the levels that we have got this working. We know those truths under those degrees of approximation as well as we know anything. And we know nature that way. So I think I'm going to stop here, leaving open how there's problems from my view in dynamics of reason, because I don't really have enough of this theory-mated measurement there. And then if there's time left, which maybe there won't be, I'll at least show you a picture of this gravitational redshift thing. So I'll just stop here. I'll do one more slide. No, I won't. I won't do one more slide. I'll stop here.
Thank you, Michael. Very rich. I wanted to ask you about this provocative claim at the end. That, there is, or at least may be, no ultimate fundamental level of physical description. I guess there is. You can hear that as some kind of metaphysical claim, or you can hear it as an epistemological claim. The considerations you adduced seemed epistemological.
Absolutely.
So, but you. The way it's written suggests something more metaphysical.
It does, doesn't it?
Yeah. I mean, that would appear to be a leap from one to the other.
So
we're constantly surprised at that the fundamental level turned out to be.
Yeah. Well, of course, we don't know that we're always going to be surprised. We don't know that we're never going to be able to get to some kind of steady state where all it is further normal science about what we already know to be fundamental. I don't know that. Nobody knows that.
No.
So the fact is we don't know what the future is.
Right.
Now, but I think it's important that the method of physics has all these other characters, including the openness to revisability along unanticipated dimensions. It's an empirical science, right? And that means it has to interact with perceptual, empirical evidence if it's going to still have the status of physics as we understand it. I mean, I know in string theory there are issues, but I would be someone who's saying it has to still be an empirical science. At least that's what I'm talking about. I'm talking about physics as an empirical science.
So just distinguishing between there is no ultimate fundamental level of description, and there is one, but we may never know what it is, or we may never know what it is in some ultimate way that closes off all further questions. Those seem to be two distinct.
They are absolutely distinct.
And I mean, you've argued for the epistemic version of that, but not for the other.
And that's all I'm going to argue for, but I think that doesn't make it any less important, because
No.
if we take seriously that physical method has these properties, and therefore there's always openness in principle to unanticipated dimensions, and further we add that what we know about the history of physics, which is that the most exciting developments have been unanticipated, right? And we've been surprised. And what to me is so amazing and so supportive of our rationality is that even though it's completely unanticipated and it even uses concepts that we didn't have before, nevertheless, we have a rational way of getting there.
Yeah.
This is fantastic. This is an optimistic, hopeful vision. But it is about the epistemology of physics. Now, we don't know what's going to happen in the future with physics. I'll say that with confidence. We don't know that it's going to settle down at something ultimate. We don't know that it's going to converge somehow uniformly at something that we can now describe from our present point of view as ultimate. We have no idea. We don't know. And we don't know that it's always going to be changing in a surprising way. I hope that it will always be changing in a surprising way, because I take that to be much more glorifying human rationality than just, oh, well, it's the same old thing again, for God's I mean, that's not hard.
But if I were to offer you the following reformulation of 5.
Okay, give me a reformulation.
There is an ultimate fundamental level of physical description, but we may never be.
But we don't know
completely
that. We don't
confident.
know there is one.
No.
How do we know that?
No, because we can say what we mean by that. And
But we don't know that it exists.
well,
How do we know
what
that
you
it
mean by
exists?
fundamental? See, fundamental is something epistemic. Then of course
I guess fundamental is also a metaphysical thing these days, right?
that's the question.
Well, I'm taking it to be.
So
Right.
if I can explain what I mean by an ultimate explainer of all properties that supervene on these ultimate explainers, then I can make sense of the idea that there is such a fundamental level of description.
And does it also explain itself,
Well,
this ultimate explainer?
what does it need to?
Well, otherwise it's a brute fact, isn't it?
No, the point is that I'm trying to make is that we can define what we mean by an ultimate fundamental.
Well, let's
level of
suppose we can.
description and say that that's what we're aiming for.
We can say that too.
Though we may never be completely confident that we've got
I have no problem with that.
Okay, so
Notice
that's
you
the
didn't say there
reformulation.
is one.
That's
You
the-
said we're aiming at it. That's a regulative ideal. Regulative ideal is fine. That's exactly Kant's solution to the antinomies. So it is a realism. It is an optimistic realism, but it's not a thing in itself realism.
I was hoping for it.
Well, you,
Right, okay. Hi. So I'm just wondering, it seems like, so when you said that the phenomenon comes last, but, so that seems theory-laden observation is
I said that in what context? Just to be clear, the phenomena comes last.
in the, well, like here, the notion of phenomena, it only comes after you've had the theoretical concepts and the,
Right, the notion of phenomena is, if you like, theory, what is the word? Theory infected, theory... Laden, that's what we used to say. Theory laden.
so usually, like, usually theory-ladenness is perceived as a problem for like, for example, nowadays there's talk of penetration of cognition and perception, and people, it was motivated as a problem towards scientific objective scientific picture. But this, in your case, it seems like it's the norm. It's this.
It's a virtue.
Right.
Without it, you don't have anything. Right.
Right.
That's because of what I mean by the theory ladenness is that we have theory-mediated measurement of a quantitative theoretical concept. Measurement is something that we perceive. It's involved with our perception. It's not, as it were, a bare, naked observation sense, and it's infused with our technology and our equipment and everything we've learned so far and accepted in science. Okay? But it is something that it is in our world, it's in our perceptual world, it's not just in our heads. And we make a lot of it, and we make more and more of it as we're going on. But that's quite different from the abstract theory itself. And the great thing is, if the abstract theory, which is quantitative, its concepts, which are abstract theoretical concepts, can be measured and assigned quantitative values in light of these measurement operations that we can perform here and now in this world, then we've got everything we could want. That's my claim.
So only the theory only supplies the theoretical, not measuring concepts. It doesn't.
The concepts,
supply-
but not the measurement
It's-
procedures,
right.
the techniques, the actual hardware.
Is it possible that two frameworks come up with competing, like there are two different competing measured results that are both not?
Sure, it's very, not only is it possible, but it's not so surprising if that happens. So again, if that couldn't happen, then it really would be a literal deduction from phenomena. But it isn't. It's just something that is pinned down. All you can use is metaphors. It's pinned down by the phenomena in a way that is firmer than a hypothetical deductive argument, which is just a fallacy of affirming the consequent, right? Or a curve fit, which isn't going to give you any of the theoretical results you want.
So how do you adjudicate when you have two competing?
Oh, you look for further measurements and further ways of making a difference. And a lot of the times we can do that.
It's in that measurement gap too. The hardware introduces some of the unexpected stuff because it's not purely theoretical. It's material.
That's right. That's right.
You mentioned.
Were you on the list,
I
sir?
don't know.
Trevor, you were next.
Trevor, who I met this morning at lunch, and we had a wonderful conversation.
Well, I mainly wanted to express puzzlement about 5, but Paul already did that. So I'll express puzzlement about 2. Just like a request to get clear on what the positive view is. So tell me if this is sort of on the right track. So it's something like the picture where the content of theoretical terms are given by the role they play in the theory, but then you add to that, there's also some thing that's offstage, how we measure those quantities, and that's also somehow like constitutive of the meaning the theoretical terms?
Well,
Is
I don't know
that-
about the meaning, but let me just give the example. So in Newton's laws of motion, you've got three theoretical concepts. Acceleration, meaning true acceleration, force, that's the theoretical notion, and mass. Okay? You can't just look up at something and say what the mass of it is, right? This is not an observation predicate. Right? So that's it. It has to do with resistance to motion and F equals ma. So his theory, if you like, implicitly defines, as far as the theory is concerned, axiomatically, those three concepts and gives some nice interrelations between them. Okay. Mass is a quantity. It can have different values. It can be equal to another mass, it can be greater or less, and then if we fiddle things out more or less, we can assign numbers to them and ratios, and we can do that. So it begins with good old Archimedes and statics and using a balance. That's just a physical thing, and this is an equality of weights or an inequality of weights. We can pile up some weights here that are equal to this weight there, and then that'll tell us the ratio between the small weight and the big weight, and that's all statics. That's not Newton's inertial mass. It's not gravitational mass, right? That's Archimedes. So that, for a long time, people know how to measure and manipulate the concept of weight, which is maybe a low-level theoretical concept of Archimedean statics, right? It's not nothing because it's Archimedes. So, so that existed before Newton. Then there's this somewhat nebulous concept of quantity of matter that became very important in the 17th century as a kind of uniform standard of this quantity that's independent of the Earth, what planet you're near or what's attracting you or even what's interacting with you. It's just, here you are, your matter. You got a quantity. It's not just your weight because it's different when you go to Jupiter or the moon. So what's that intrinsic quantity? Well, a lot of people thought it has to do with the absolutely dense matter in proportion to the vacuum. That was a popular mechanical view. As I said, that gives you a precise mathematical meaning. The only problem is, how in the world do you tell what that is in any given body around us? You have a super microscope that's going to look into this thing and measure its vacua? No, at least not then. Okay? So there's a perfectly fine concept, but it doesn't have measurement linked to it. Weight from the beginning has a measurement linked to it. So Newton introduces this new concept, inertial mass, this resistance to an arbitrary force. Okay? And he's saying this is something that we can use to connect the other concepts and eventually to measure, like everybody wanted, and compare the masses or the quantity of matter in the planets and the quantity of matter in me and you and so forth. And through all these complicated interrelations and the way the theory is intertwined with the things that we can measure, as opposed to things that we can't yet measure, we now have theory-mated measurement of mass. So that's, I think, the best worked out example I've got. And that's what I mean.
So, am I wrong to? So, are you theorizing about the semantics of theoretical terms in general, or are you just trying to make claims about like particular concepts and particular?
I'm not talking semantics. I'm talking epistemic access to the theoretical concept. So, for example, the percentage of solid matter versus vacuum is a nice concept. We don't have epistemic access to that at the moment. I'm sorry to say, so let's try something else. Okay? What do we have epistemic access to? Well, we got weight. Everybody agrees with that. We also observe what's going on in the heavens, and we have Kepler's laws, let's suppose, to make things simple. And so we know that the Galileo acceleration field property can actually extend there. Of course, now it has to be at a given distance, and it's an inverse square thing. But then the moon test shows you that that actually hooks up completely with weight.
So now I'm confused what the alternative to your view would be. If it's an epistemic access, how could that not involve some what's the
Precisely. But the problem is the problem is to explain and appreciate what a tricky and interesting matter it is to do that. That's my substitute for the Kantian schema. Perception systematically linked with conception. two different things that have to be linked. It's not semantics. Like for Kant, it's about how the hell do we know stuff? Okay.
Yeah, I was also interested in theory-mediated measurement, and in particular, just sort of not entirely clear on how it gets to be more secure than the other things you mentioned. I mean, just naively, I guess the notion of theory-mediated measurement makes complete sense to me, but I'm finding the security of a theory-mediated measurement would depend almost entirely on the security of the theory that backs the theory-mediated measurement.
No, those are connected. The
And
security
then-
of the
then
theory.
then the question
I'm
is,
sorry.
where does the, what's the basis for believing the theory? Well, if it was something like induction or abduction or co-fitting or hypothetical whatever, then presumably a theory-mediated measurement wouldn't be more secure than things made by those methods. So I guess there must be something about the special kinds of theory involved here and the special kinds of security that they have, or is it something else?
Yes, good, good. Thank you for the question. I'm sorry for interrupting you too soon. Okay, so Newton has these concepts of force, mass, and true acceleration. And given those concepts and given Kepler's laws, you can establish the law of universal gravitation by something that is more than a hypothetico-deductive argument. It's also more than an induction from merely observational stuff. And it seems to be more secure. Why? Because it has this ability to have these sequence of approximative measurements that are capable of being improved step by step, and every step you take makes it more secure than it was before. But it also explains the limitation of the approximation more precisely than ever before. So that's something, obviously hypothetical deductive is not secure at all by itself because it's just a fallacy, right? Curve fitting might look a little better, but with curve fitting, you're not going to reach the theoretical value you get out of those Newtonian concepts, and in particular, determining what is the true world system. That is, what is the center of motion in the solar system? Right? You're not going to do that simply by doing repeated curve fits of the kind that, at least people say with some falsehood, Kepler did. You've got to introduce some concepts like mass, force, and acceleration. Obviously mass, because it's the center of mass that matters. It's the true accelerations that we want, not just the relative accelerations. And it's the forces, the real forces, not the pseudo forces that we want.
I guess I was thinking that even with curve fitting, if there's some kind of intervening variable in the curve, postulate the relationship between x and y by some other parameter z, then you're going to get something like this phenomenon. We're going to be able to
Yes,
on x and y,
yes,
get z,
yes,
and z will
yes.
be used to make predictions.
Yes,
You get this kind of
yes.
iterative support.
And you can do a kind of Woodward Pearls kind of method of equations, simultaneous equations and causality. Yeah, that would be something that has some of the properties of theory-mediated measurement.
Actually, maybe I'm just going to give myself a...
I'm glad that you are doing so, too. I would be very
Because
unhappy
I was
if you
going to
did.
ask very much Dave's question, and I'm a little puzzled by the answer. The structure of the Principia is definitions, which are nice, the scholium on space and time, which is quite beautiful, and then here are three laws, bang, bang, bang. These are not deduced from anything. You don't notice any phenomena. They obviously have a lot of content. If you compare Galileo's notion of circular inertia, Newton makes a different choice for what a fundamental state of motion is, and therefore gets a different notion of a change of state of motion. So from that point of view, it looks very hypothetico-deductive, where the hypotheses are the first three laws, and then, of course, very intricate deduction from those to get the exact form of the force law for gravity. But what you said about security was, well, hypothetico-deductivism is not secure, it's a fallacy. I think that's a pretty direct quote.
It is a direct quote.
Yeah, but by a fallacy there, you just mean that it's not logically valid.
Right.
But none of this is logically
None of
valid.
it is
So
logically
you
valid.
can't point at, you could point at any of these and say they're just fallacies, so they're not. So that can't be a correct. I mean, I
I'm
don't
afraid
see
you
why
got
this-
me there, Tim.
Hmm?
I'm afraid you've got me there, Tim.
Yeah, so I'm not sure why the ultimate security isn't more or less from looking at it at a large scale. It is a kind of HD. I mean, it's a very complicated and intricate and beautiful large-scale argument, but somehow at the basis of it, where the laws come from is they spring fully armed from Newton's head, and then they do their work in guiding the deduction that gives you the precise force laws. And the ultimate justification for believing it all is that it works so well.
Excellent. Unfortunately, it's not quite right.
Okay.
Now, they don't just spring de novo from Newton's heads. There are, first of all, what does he rest? He gives a little scholium to those laws, which is his argument for them. And he calls attention to both the fact that these cover cases that are already accepted. Galileo and projectile motion. Of course, he's taking it to be linear inertia, which was pretty much accepted by everybody, especially Huygens, who was very influential for Newton. There were also the impact laws of Wren and Huygens and so forth, conservation of momentum. So all of that was there before Newton, and he's kind of co-opting it now. That's one piece of input to his formulating of the laws. And the second piece is that he himself does some very detailed experiments with these incredible pendulums made out of glass and wool and wood, and they're really long, and there's all kinds of conservation of momentum, things that are, proved to tiny little decimal points. So there is evidence that he himself experimentally refers to. But you're right, in the end, there's something more, namely the success, and this is the part that you're now talking about, in making possible these theory-mediated measurements that allow this process, this Newtonian style process of successive, ever more accurate approximations to proceed. So there are three dimensions to the status of those laws. Actually, we just had a nice thesis, but done by somebody at Stanford, not because of me, but because George Smith visited, and he worked with George Smith about it, and he isolates these three different sources of epistemic warrant, if you like, for the laws. And the third one is completely forward-looking, but it's not nothing that it is anchored in what already existed, including statics, because statics is all subsumed there, too, in that same scholium, right? As now thought of as a Newtonian force.
Right.
Okay. So, so you've got things that were well established before Newton in everybody's eyes, were not controversial. Okay? Nobody at that point was worried about the law of inertia being circular. Nobody was denying conservation of momentum. So all of that was accepted, and everybody accepted that this way, unites at least part of dynamics with statics. Right? So we've got all that just in what we already knew, plus his experiments. Now, but ultimately those laws of motion have to prove their mettle in this process of successive approximations and corrections. Okay? Now, I am saying that process of, you might call that just a fancy sequence of HD inferences, but it's precisely it being a certain kind of fancy sequence that gives it the extra power. It's not like you're saying, well, it just follows, but it's also simple. Oh, it's not ad hoc. Oh, it's very accurate. I mean, you have to do better than that. And what you do better is the sequence of approximative improvements which depend on theory-mediated measurement against the background of those laws. Now, of course, eventually, it allows you to change those laws, first in special relativity, and then in general relativity. Those laws are modified for good reason. But it's still continuous with what went before. And the Newtonian laws remain valid in the domain that isn't relativistic. I mean, they're approximately enough true that we don't worry about it. So that seems to me, it's at least adding a whole bunch of structure to the hypothetical deductive method that wasn't there before. And that's, together with what we already knew, is something, what it says is that the confirmation process is necessarily historical, and that it involves a temporal sequence of improvements over time. So it's not just a logical kind of problem of underdetermination thought of in a purely logical way. That's not going to get you anywhere. So,
Anya, you
This is really just a small thing following on.
a small thing from you, Anya?
No,
I'm
really.
skeptical.
Yeah, I mean, there's also. I mean, my real question was how exactly your notion of schema maps onto Kant, but maybe that's rather for, you know, a more private conversation. I don't want to bore anybody else to death, but when I wheel out my Kant stuff. But I just wanted to see if I really understand how the example is supposed to work, because I still don't get. So the suggestion is we have a theoretical concept and we now somehow want to know how to apply this in the world, and I there see the connection to the Kantian account. That's exactly what he thinks that a schema is.
Exactly.
But like Trevor, I had trouble seeing what in our example actually the theoretical concept was that didn't already have built in the application conditions, and that, you know, there wasn't anything extra that I had to add. So I do understand the structure of the example. So the theoretical concept is supposed to be this quantity of matter thing, which then, with the help of, you know, the notion of gravitational and inertial mass, you can eventually measure. But I wasn't sure how I could ever apply any of these equations to the notion of matter in play in this quantity of matter concept. So the quantity of matter was supposed to be the ratio of the volume.
Well, that was one way of explaining it in a way that was independent of motion, independent of weight, and so on. That was one theory.
Right, but then I just wonder how you can bring them together. That just seems like cheating. How
Well,
do
I don't want to
know?
bring that in. I don't want that to be the right theory.
No, well, I mean, maybe I should just finish what I
You
was going
finish.
to
I'm
say. but
interrupting
no,
again.
that's okay. So just so the theoretical notion was the proportion of the volume to the amount of matter of an absolutely dense body or something like that.
Yep.
And in order to get a handle on how to apply that, you're now suggesting I basically just plug in my Newtonian equations somehow for the amount of matter of the absolutely dense body. So I have to assume that this is either already inertial or gravitational mass, otherwise I couldn't use the equation there. But then I don't have a completely theoretical concept anymore. I already have something that's defined in terms of acceleration, which I can directly observe. So I wasn't quite seeing, you know, how this was theoretical, and then I do some stuff, and now I have something that I can actually measure. It seems like I'm just assuming that there is this notion of mass that I already know I can measure after I've done my Newton. So it wasn't really theoretical, so it was sort of measurable already when I started.
Okay, good. First of all, when I gave that, you know, song and dance about the ratio of the vacuum to the absolutely dense, or whatever way it's done, that was just an example of how their quantity of matter is supposed to be, is a relatively vague concept as people were using it. That is, it's the amount of matter that it has independently of how it's interacting with anything else, independently of how much it weighs here and there. It's just an objective, intrinsic property of the body as such. Okay? That's a constraint on what we want from quantity of matter. And it should play some kind of role in the physics that we're trying to build. One way to think of it quantitatively is in terms of the atoms in the void picture. But that's not a useful way to think of it because there's no way to measure those little vacua. We don't have a handle on them, okay? Right, so is there some other concept that has the properties of quantity of matter? It's a kind of invariant property of the body, unlike weight. Okay? And also it has it whether it's moving or not. Right? It's just, that's the stuff in the body, okay? Newton didn't take the concept of inertial mass, he invented it. There was no concept of inertial mass before Newton. There was concepts of weight, there were concepts of quantity of matter, there was no concept of mass in Newton's sense linked to inertia. Okay, he introduced that. It turns out that concept can be shown to give you all the properties you wanted from quantity of matter all along, and furthermore allow you to do real physics and allow you to measure it in all these different ways.
Okay, I mean, I see the way it's supposed to go, but why couldn't I mean, Newton couldn't have picked this one, but couldn't I have just been using, you know, whatever measurements we now have to determine, I don't know, spin or some other intrinsic
Well,
property?
that would be
I
a
mean,
pretty
if the
good
only-
feat to use spin.
Right,
sorry,
but
I'm
I
being
mean, so
silly.
the only description we have there, it's some invariant intrinsic property of the body, and then we say, oh, why don't we use this one as what, you know, makes the application of that concept possible? I don't know, so it seems like there's lots of other invariant properties in physics that might, you know, fit the description.
Well, of course, there was no spin at that time. But
No, I know, but
forgetting about that,
in general.
forgetting about that, Newton does show that inertial mass has the properties relative to weight that we wanted quantity of matter to have.
Oh, so we're assuming that a certain,
Well, we think there is weight, but we think weight is not an intrinsic property of the body because it depends on where you are.
oh, so but
So
we're
what's
assuming
the
that
property
that's
of
a
the
connection.
body that explains, when you plug in where we are, what it weighs?
Okay,
That
but
is,
this
what
would
is
be-
its tendency to move toward that thing?
But this is an additional piece of information that we didn't have, that there actually is supposed to be a connection between quantity of matter and weight.
Well, everyone thought that.
Well, okay, but then I think just,
I'm sorry, everyone thought what? I just,
That there was a connection between weight and quantity of matter.
right, but can I just?
Yeah, I'm
intervene for
done.
1
You
second,
take it from me, yeah.
which is that I take it before Newton, nobody even imagined that weight depended on location. Why would they?
Well, they knew things about how there's variation in gravity depending on where you are and how high you are, you know, with those kinds of experiments. So they knew those things with pendulum experiments. That the weight,
You can
if
get
you take a
variation.
pendulum up into a mountain, it's going to have a different behavior than if it's down at the surface.
You can measure that?
Oh yeah,
They could measure that?
absolutely, they could measure that.
That's-
They were good.
I'm-
They were good. Huygens, this is Huygens, man. He could do those things.
But how could, I don't even understand how that's, no, I don't understand. how
Because the oscillation depends on the
But what are
gravity
you
that's
using to
acting on
measure
it.
What are you using to measure the time of the oscillation?
Your favorite watch or your favorite way of measuring
But
time.
you think that there were mechanical watches?
I'm not
that were
saying
accurate
that.
enough
I'm
at
not
that
saying
time for
that.
people? No, but you're making it sound like someone did an experiment like Torricelli. with-
Well, they did
with
things like
pendulum,
that. They did
with
things like
pendulum, and saw differences. in
Huygens did things
gravitational
like that,
field.
yeah. The length of the so-called seconds pendulum would vary. I'm sorry, I don't remember exactly how all that was figured out, but they did do that.
Wow. Oh, I'm shocked.
I'm still trying to understand this theory-mediated measurement, and if I understood you correctly, you just elaborated that it differs from hypothetical deductive understandings of the formation of theories in that it is not as radical. There is a more incremental, more continuous progress in how these theories are developed. How would you say does it differ from curve fitting? Because I can fit curves quite, I can make very small changes to my functions of the curves. Could you just elaborate how it differs from curve fitting so that I understand?
Okay, good. First of all, it's not theory-mated measurement as such that is more secure. It's that theory-mated measurement enables more secure inferences to the actual theory. Right? So it's not the theory-mated measurements are more secure in that they're, as it were, better measurements, but they are measurements that involve understanding the relationships between different aspects of a theoretical concept like quantity of matter. Right? And I'm saying theory-mediated measurements are essential for this more secure method of inference, because it allows theoretical concepts to be, if you like, part of a curve fit. Would be a crude way to put it, right? That is it's a little bit like the example that Dave was talking about, where it looked like the Pearl kind of intervening variables, treatment of causality and of those kinds of equations, could be an example of something more than curve fitting, but something pretty close to it, because it introduces some variables in between there. And those variables have got to have some stated relations to what you observe. And that's what the equation gives you. So what you don't have is a curve fit where all you're allowed to do is look at, as it were, the observational predicates that are distributed over space and time, and then find the simplest curve that fits that distribution. Because you've got to get some kind of theoretical concept in there to get the thing that I'm talking about.
So about why? I mean, I could also just change the parameter without having any theoretical commitment to why I change it, just because it fits better. And then I try to find the best theory of that.
Well, but at least in the, what do you mean by the parameter? I mean, if it's a parameter in a Pearl's type theory, then you have to have certain linear equations governing it.
Yes. I don't have any particular understanding of parameter. I'm not firm with Pearl.
But if you mean a completely observable property that is then going to be linked by some kind of induction to other ones, without yet having any theoretical thing to stick in there, you're not going to get the same thing you get with theory-mediated measurement, even of this Pearl's type.
Could I interject
Sure.
something in here? With curve fitting, it's independent of what the instrument is. It's just a mathematical technique. With a theory-mediated measurement, each one of these relates to a particular instrument that's based on that theory, so that when you get feedback from your curve fitting about that, you can go back to that particular instrument and make an adjustment. If you have three different kinds of instruments making these measurements based on different theories, your curve fittings will have different results. They're very specific to the theory of the design of that instrument. Otherwise, you have no difference, right? I mean, curve fitting, you could get there, but you wouldn't know what you've gotten to, you wouldn't know what you've affected, other than getting more precision without any actual reference to a theory. But with theory-mediated measurement, you have an instrument that's also based on the theory as well as the theory and the math.
I buy that.
By the way, the first observation that gravity varied at different points on Earth was made in 1672 by Jean Richet, who took a pendulum clock to Cayenne, French Guiana, and found that it lost 2.5 minutes per day. In 1687, Isaac Newton explained this by explaining it in terms of the Earth having a slightly oblate shape.
So he compared astronomical time to pendulum time.
Okay, so that's the clock that they had. That was
They had a big
accurate
clock.
that they took.
They had a very big clock. It wasn't a
That
wristwatch.
makes more sense.
It does make more sense, doesn't it?
Yeah.
And that
Thank
was
you.
15.
What would we do without Google?
I know I've been favoring this side, so let me just.
Oh, maybe I wanted to offer an interpretation of the question asked by Professor Anya.
Yarnish.
That I think she was pressing you on sort of absence of conceptual necessity in the development of science. Kind of, that was my understanding.
That's
And
something one could
you
do,
seem to
yeah.
be completely happy with that. You don't claim that it was conceptually kind of necessitated.
Exactly.
Okay.
We have been very, very lucky and very, very good at dealing with our good luck.
I have a question, but also want to add something. So, in terms of like intrinsic mass and gravitational mass, like you measure gravitational mass, there's like the pendulum stuff, and you measure intrinsic mass in order to do with like slit experiments and like the Broglie wavelength.
Okay, well now we're in another theory
Yes, sorry, so like the like mass, intrinsic mass is done more with like matter as a wave-like thing.
That's modern quantum physics.
Yeah, so it has more to do with like, there's no reason why that mass and the gravitational mass should be the same, but it happens to be experimentally the same, so it was a logical leap to connect those two things, and they just happen to be very similar.
That's interesting.
So like, but you do have to have a conceptual jump there, because there is no reason that like a wavelength of
Right.
matter has anything to do with
Yeah.
the space-time curvature. Then my question is more to do with like, there's theories where there's like interpretations that are kind of like unprovable either way. One example would be like the collapsing of wave functions. So there's like the Copenhagen interpretation, and there's also like the de Broglie interpretation, and both sort of like are correct, but the only reason the Copenhagen one is chosen is because like you can do statistics easily on like collapsed wave functions, but you can't do any math with respect to like hidden non-local variables. So it doesn't really, neither one really gives you like a satisfactory answer, but they're both like correct, and one is just more like useful for physics, and so we choose that one. But like, so how does this like historical theory mediated measurement deal with like some sort of like impassable interpretation problem like that?
Well, that's where the idea that we have a certain kind of abstraction, a certain kind of abstract structuralism being deployed to say that we're going to describe the mathematical structure that we can measure and access now. There could be all kinds of hidden stuff behind there that really explains it. We don't know yet about that. And if there are different ones that give the same empirical results, well, then we just say we don't know. But the idea of it has to do with this distinction Einstein made between principal and constructive theories too. That it's one thing to look at the laws that gravity obeys, as Newton puts it, without knowing what gravity is, without knowing what its true nature is or its true cause is. And he says it's enough that it obeys these laws. Now, those laws, the claim is, are very well testable and in a certain sense established within certain experimental limits by theory-mated measurements. And so by making that abstraction, we avoid having to answer the question of, well, what is the deeper explanation?
I have a public service announcement in relation to this question, which is that the account of the relation between Copenhagen and the de Broglie pilot wave theory is propaganda produced by the Copenhagen people, which will be spoken about by Adam Becker on Tuesday, next Tuesday, in the Metro Area Philosophy of Science series, which will be here at NYU, in this building, I think.
So in this very room.
No, downstairs.
No, it's downstairs. So that's just, this was not about quantum mechanics, but if you're interested in quantum mechanics, next week there will be things on quantum mechanics. I think there was just one other person who I saw, and we only have time for one more, so let's just make that the last one.
I use nothing as infinity. Can infinity define theory?
I'm sorry, could you just repeat that? I didn't quite
If I
catch
use
it.
nothing as infinity, can infinity define, decode theory?
Are you saying if affinity equals 0?
Yeah.
That's a problem. I don't think infinity equals 0, but infinity is certainly mysterious.
Yep, it is. Or nothing.
So is nothing.
Nothing is also mysterious.
Yeah.
Well, I can't argue with that.
Yeah, right. So yes, the nothings and infinities, which clears all that up. That's all the time we have. Let's please thank.